Welcome back to ICM PMA 2022. We now move on to the second session on photonic materials and devices. To chair this session, we invite Dr. Riju C. Isaac, who is an associate professor in the Department of Physics, Cochin University of Science and Technology, CUSAT. He obtained a PhD in pulse laser matter interactions in 1998 from CUSAT. He was also involved in related research areas including nonlinear optics, thermal lensing, photoacoustics in liquids, and development of dye-doped polymers as suitable laser hosts. Later, he was visiting fellow at the Department of Nuclear and Atomic Physics, Tata Institute of Fundamental Research, Mumbai, where the thrust area of research Dr. Riju C. Isaac was involved in was the development of X-ray sources of sub-picosecond duration suitable for phase contrast imaging of biological samples. Early in the year of 2000, he joined the University of Strathclyde as a research fellow, where he later became a senior research fellow. Dr. Riju C. Isaac has taken the lead role in design and construction of a 10 meters long laser wave field accelerated mega electron volt electron beamline and the vacuum delivery system for TW femtosecond laser pulse. He has developed ultra-short VUV, X, and gamma ray sources suitable for biological imaging using TW laser system at Strathclyde and petawatt laser system at Rutherford Appleton Laboratory, Didcot, London. One area of investigation was the study of the effect of ultra-short mega electron volt beams on malignant tissue to help the treatment of cancer and advancement of oncology. At CUSAT, Dr. Riju C. Isaac currently pursues research on 3D printed polymer microscaffolding for tissue engineering with collaboration from biotechnology and polymer science. Dr. Riju C. Isaac has more than 60 international publications and H index of 25. The main area of expertise are femtosecond lasers, ultra-short laser matter interactions, laser wave field acceleration of electron, laser-derived VUV to X-ray sources, and laser-driven sources for biotechnology and imaging. Dr. Raju C. Isaac, we are honored to have a personality as esteemed and experienced as you here to chair this event. Dear sir, I request you to start the conference. Sir, you may unmute your mic and start speaking.
Okay, thank you. Thank you very much. Without much of introduction, I think we're a bit late already. Let me introduce the speaker. We have one plenary talk and 3 invited talks in this session. The plenary talk is by Professor Laetitia Petit. We listen to Laetitia Petit on the novel glass-based materials for biophotonics applications. And, Dr. Laetitia is a professor in the photonics laboratory at Tampe University, Finland. Also an adjunct professor in the Faculty of Biomedical Sciences and Engineering, adjunct professor in the Inorganic Chemistry Laboratory at Abo Academy University, Finland. Dr. Laetitia received her PhD in Material Science from the University of Bordeaux in France in 2002. Her current research interests include the processing and characterization of novel active glasses, glass ceramic, and fibers for photonic applications. Then she focuses her research on understanding composition, structure, property relationship to suit specific application in photonics. Dr. Petit is a co-author of 2 patents, more than 160 referred publications, reviews, proceedings, and book chapters. Also, there are more than 20 invited and contributor presentations in her career. A warm welcome to Professor Laetitia. Over to you, Professor Laetitia. Thank you.
Thank you for the introduction. And can you confirm that you see my screen?
Yes, we see.
All right, perfect, great. So, so good afternoon, everybody. So it's from Finland. I would like to first thank the organizer because this is a great opportunity for me to actually speak about the research we do at Tampe University in Finland on the glass-based material for photonics, but also for biophotonics. So few words about Tampere University. So we are about 2 hours away from the capital, Helsinki. So we are located here. And we merged in 2019 with the University of Tampere. So it was the Tampere University of Technology, and we became Tampere University. So now we have about 30,000 students, more than 300 professors, and more than 4,000 employees. The Tampere University is divided in 7 faculties, and my group, Photonic Glasses, is in the Faculty of Engineering and Natural Sciences. So the research we do in my group is we develop new, I will say, biophotonic glasses from the UV to the mid-infrared application, so mainly the laser and the photosensitive photoresistant glasses. So we go from the material development to fiber thin films and then to the device. We try to understand the composition, structure, property relationships in this material. So we want to actually tailor the glass composition to suit specific applications. And today I'm going to present some of the applications that we were targeting and how we actually design new glass composition for this. So in terms of material development, so we are doing glass-based material, so from melting or sintering process. So today I'm going to speak only about the melting process. And from these glasses, we try to make particle-containing glass or glass ceramic. So the glass ceramic, as we probably all know, is we try to in situ grow using a thermal heat treatment crystal in the glass. And as we cannot control the crystallization process, as you will see in this presentation, so we have worked on the direct doping method. So it's we prepare crystal, we dope them with the rare earth ions that we want with the specific composition, and then we add them in the glass. So this is what I call this particle containing glass. So they are not glass ceramics. In both of these materials, what we try to have, it's crystal doped with the rare earth ions, and they should be homogeneously dispersed in the volume of the glass, and this is our target. So we have worked a lot with fibers, as I said, one of the applications is for medicine, because this fiber, this optical fiber, can find application in the laser ablation for surgery, for photodynamic therapy, for cancer treatment, sensing, imaging, spectroscopy. However, most of the common use fiber, if they are used in vivo, so inside the body, you need a second surgery to remove them after use. And this is the reason that people have been working on bioactive glasses. So this specific type of glasses, they react with the living tissue, and they will form at their surface a layer, hydroxyapatite layer, with the same composition and structure as the mineral face of bone. So you have here on this table the most used bioactive glasses, so the 45S5 and the S53P4. They're also commercial glasses, and they are silicate. So you have their composition in weight percent here. The problem with these glasses is they crystallize upon the cooling or the heating. So that means that we cannot draw fibers from them. So this is the reason that we have worked on this development of new biophotonic glasses. And one glass system that is quite suitable for this type of application is the phosphate glasses, because you can change or tailor their composition, so you can tailor their thermal properties, so you can draw them into fibers. For us, we decided that to be a good candidate for fiber drawing, they should be, of course, thermally stable, and we use the difference between the onset of crystallization and the glass transition temperature, and we said that it should be at least 90 to 100 degrees C. So for the glass to be considered as a good glass former, so no crystallization should occur during the fiber drawing process. You can change the glass composition, so for the glass to be bioactive, and they will, the phosphate glass, they have this congruent dissolution, so they actually dissolve in the body layer by layer, so the composition of the glass actually doesn't change over time as compared to the borosilicate. And these phosphate glasses, they can, they have also, they are well known to have this high rare earth solubility, so they are very good candidate for optical application. So let me discuss about what we did with this erbium doped phosphate glasses. So these are the two glass systems that I decided to speak about today. So it's the first one is a phosphate with sodium and strontium, and then the other one is with calcium. So the glasses that we do in my group, it's a standard melting process. So we melt, quench, and anneal the glasses. So let's start first with this glass composition. So back in 2017, we made the first fiber, so erbium, ytterbium, co-doped phosphate glasses. And we were able to draw actually fiber using a drawing temperature of 550 degrees C. And here's the image, the SEM image of the fiber. And we measured losses at 0.2 dB per centimeter at 1.3 microns. So our goal was not to reduce as much as we could the losses, it was just to prove that we could draw this fiber, this composition into fibers. We measured, of course, the thermal properties of the glass prior to and after the drawing, and we found that we have a small decrease in the glass transition temperature after the drawing. So we try to understand this with the structure. So we look at the infrared spectra of the glasses. So in red is the preform, in blue is the fiber. And we saw very, very small changes in the structure of the glass, as you can expect, because the thermal process, the drawing process is a fast process, and it will induce only stress. And what we think is happening is we have just some reorientation of the POP bonds, and that might explain the small changes in the thermal properties of the glass. And then we look at the absorption property of the glass before and after the drawing. And this reorientation of the POP bonds has no impact on the rare earth sites. And so that confirmed that we can actually draw this this glass into fibers. However, when we spoke with our partners in the Faculty of Medicine, they want to have as little as possible of the rare earth content. So, and ytterbium is in a quite high concentration, so they ask us to actually work on the glass composition to reduce the rare earth amount. So what we did, we went to erbium doped with a low amount of erbium, and then we try to increase the spectroscopic property of the glass by adding zinc, aluminum, or titanium. So here you have, and it's a systematic study way to characterize the glasses. So we do the thermal properties of the glass, and when we add aluminum and titanium, we increase the glass transition temperature. So we use again the infrared spectroscopy to compare the structure of the glasses. So when we change the glass composition, so when we add aluminum, titanium, or zinc, we have a depolymerization of the glass network, as evidenced with the decrease of this band here and of this one as compared to this one. And so we have less Q2 units and more Q1 units. So it's the units forming, so these units here, they are forming the phosphate network. In the case of aluminum, alumina and titanium, so what is happening is we break the POP bonds and we create some new bonds, PO, AL or TI bonds. And it's because of the formation of these bonds that we have an increase of the glass transition temperature. Zinc in this case, because it has no impact on the glass transition temperature, is expected to act as a modifier and not as an intermediate. So we check the spectroscopic property of the glasses, and changing the glass composition has almost no impact on the intensity nor on the lifetime of the first excited level of the erbium, except for zinc. And so zinc seems to be the most promising glass because it has a long lifetime of the first excited level and also a higher emission at 1.5 microns. So this is a typical emission spectrum of erbium centered at 1.5 micron when we use an excitation at 980 nanometer. So the reason for that is because we think that depolymerization of the phosphate network is actually increasing the distances between the erbium ions in the glass. So we try to do some glass ceramic. So it's to in situ grow crystal in the glass. So we use a two-step process. The first one is the nucleation. So we do a heat treatment around the glass transition temperature for 17 hours. And then we increase the temperature near the crystallization temperature to grow the nuclei into the crystal. And then we look at of course, at the cross section of the glass. So this is an example. So this is the reference glass, so the phosphates, strontium, and sodium. And you can clearly see that we have this surface crystallization and we have this amorphous part in the center in the volume of the glass. And then we use a scanning electron microscope to confirm that we have surface crystallization, so the crystals are growing from the surface. So as I said at the beginning of this presentation, we want the crystal to be in the volume of the glass. So this is not the way to go to try to increase the spectroscopic property of the glass. So we went back to the composition with the zinc. So we tried to do this core clad fiber. So the core has this composition. So the zinc, because it's promising, and this 0.25% more of erbium. And then to reduce the refractive index, then we did the cladding with a lower amount of zinc and no erbium. So you have here the refractive index of the core or the glasses used for the core and the cladding as a function of the wavelength. And we have Na of the fiber of 0.09. So the cladding was prepared using rotational casting. So you cast the cladding in the mold and then you spin really fast, and then you have this hollow tube as shown here. Then we used the rod in tube technique to draw the fiber, and the fiber was obtained using a 980 degree C. So here's the near infrared image of the fiber. So the core diameter is 47 micron and the total diameter was 120 micron. And we got 2 dB per meter losses. So the low attenuation loss and the proper light propagation confirm that the light is confined along the core. So we did some in vitro testing, so very simple experiment. So we immersed the fiber in SBF, so simulated body fluid. This liquid has the same elements that in the blood. And we track over time the emission property of the fiber. So this is what you have here. The fiber was immersed up to 28 days, and you have the emission band of erbium, the typical emission band of erbium, centered at 1.5 micron. And over time, we decrease the intensity of the emission from the erbium. So we used the scanning electron microscope to look at the surface of the fiber at different data points. So here you have the fiber after 2 days in SBF and then 28 days in SBF. And the surface of the fiber actually changed, and also the diameter of the fiber is reduced over time. So this clearly showed the reaction of the fiber with the liquid. So we use EDS, so elemental dispersive spectroscopy, to analyze the surface of the fiber. So here you have the expected composition for the cladding, and then the composition of the cladding after 2, 4, and 28 days in SBF. And we notice the presence of magnesium, chlorine, potassium, and calcium at the surface of the fiber. And these elements are actually the one from the SBF solution. So this is a clear sign that we have this hydroxyapatite layer, so this calcium phosphate reactive layer, confirming that even if we added some zinc and erbium, the fiber is still bioactive. And so we did the experiment at 28 days at 37 degrees C, so the body temperature. And then we have a faster reaction, so a larger amount of calcium, and the fiber is way smaller also. And this is so indicating a faster reaction rate in SBF at 37 degrees C, as you can expect. So this is a promising glass composition for tracking in vivo the reaction of the glass with the body. So then we worked on the upconversion application. So it's how to convert the mid-infrared to visible light. And this could have different application for solar cell application or biomedical application, for example. But we need to work on the new glass composition because you need to have this low phono energy. So this is the well-known table of phono energy of different glasses. And so, of course, the germanate, telluride, the fluoride, and the chalcogenide are good glasses, good glass candidate as a low phono energy. So we decided to work with this oxyfluorophosphate system because they have this good chemical stability, large rare earth ion solubility, low phono energy, and low processing temperatures. So here's the composition that we have worked since 2016-15. So it's a sodium phosphate with calcium oxide and calcium fluoride. And you have here the picture of the glasses after heat treatment. And we found that depending on the glass composition, we don't get the same type of glass ceramic. So we found that an increase of the calcium fluoride crystal increase the polymerization of the network and decrease the crystallization tendency of the glass. So we use the SEM to try to understand what's going on. And then we have, of course, different crystalline phases growing in the glasses. And then we found that the glass with a large amount of calcium fluoride has this bulk crystallization with calcium fluoride crystal. So, which means that it's probably a good candidate for upconversion application. So we did the glasses with erbium, and then you have here the normalized emission spectra, so the same using a 980 nanometer excitation, and we have this broadband, and it's typical of erbium in amorphous network. And here you have the intensity of the emission at 1.5 micron, and then you have a decrease when we increase the concentration of calcium fluoride due to the low phono energy. But because of that, we have an increase of the intensity of the upconversion spectra of the glasses, and specifically for the glass with the large amount of calcium fluoride, so low phono energy. So we did the heat treatment of the glasses using again this two-step process, and here you have the picture of the glasses after heat treatment. So from no calcium fluoride to only calcium fluoride, no calcium oxide. And you can see that the glasses, they look completely different after crystallization. So they have here, they are opaque and then they become more transparent glass ceramic. So we use the XRD to try to identify the crystal. So all the glasses with calcium oxide and calcium fluoride, they have different peaks related to the different crystal. But the glass prepared with 25 mol% of calcium fluoride exhibit only few peaks, which are related to the calcium fluoride crystal. We use it again, and we found that we have this surface crystallization for all of the glasses except the one with pure calcium fluoride. And as for the under glasses, we have this calcium fluoride crystal growing, precipitating in the volume of the glass. So it's still, again, very promising. So we look at the upconversion spectra of this glass, and prior to in black and after heat treatment, and we can see a huge increase in the intensity of the upconversion, indicating that the erbium ions are actually entering inside the calcium fluoride crystal. So this is a very promising glass for this type of application. However, when we look at the thermal properties of this glass, so this is the one highlighted in red, the delta T, so the difference between the onset of crystallization and the glass transition temperature is really small, it's only 50. So it's impossible to try to draw the fiber from this glass composition because it has a poor stability against crystallization. We have also some other issues with this glass composition. So the first one is the loss in fluorine. So it's well known that fluorine is a volatile element. So we try to, we prepare the glasses using different melting temperatures. So from 900 to 1000 degrees C. And then we quantify the losses in fluorine. And why I'm showing this is because it has a huge impact on the transparency, or the losses in fluorine has a huge impact on the transparency of the glass ceramic. All of them have this calcium fluoride crystal dot with erbium, but the transparency is completely different. So the crystal growth is different and depends on the fluorine content. The other problem with this glass is it's an hygroscopic glass. So just to show you why it's an issue. So here it's the upconversion of the glass in black when it's freshly crushed, because we do the measurement in powder. And in red is after 4 days of storing the glass in normal atmosphere, so not in desiccator. And we have a huge decrease in intensity of the intensity of the upconversion. And after 6 days in normal atmosphere, we could not actually measure the upconversion. So this is also an issue here, this hygroscopicity of the glass. So what we try to do is to increase the thermal stability of the glass. So we try to first work on that. So we added a larger amount of erbium, and so we try to have this clustering of erbium ions, and then we can further increase the upconversion property. So here are the glasses that we prepared very recently. So we use 2 different erbium precursors, so erbium oxide and erbium fluoride. And you have here all the thermal properties, and especially the delta T. And when you increase the erbium content, you increase the thermal property, and this is due to the strengthening of the glass structure. And the erbium fluoride glass is actually more stable than the erbium oxide. So for the moment is what it's the most interested in. So we did some XRD analysis. So after the heat treatment, we try to do the glass ceramic. And we do have the calcium fluoride crystal in all the glasses, but when we increase the erbium content, then we have also some other crystal growing. But more importantly, we have here the upconversion spectra of the glasses after heat treatment, and we increase a lot the intensity of the upconversion after heat treatment. And so confirming that even if we have some small low amount of calcium fluoride crystal in these glasses, the erbium is still going inside, and then we have a lot of this green and red emission. And the red emission is higher than the green as compared to the glasses prepared with a low amount of erbium, and we think it's due to this interionic interaction leading to efficient cross-relaxation process between the erbium-erbium pairs. But the glasses with high concentration of erbium are actually quite promising, and we are now in the process of drawing them into fibers. As I said, we are working also with a direct doping method. So we prepare crystal, and then we add the crystal in the glass. So and you have the process of the glass melting here. So we melt the glass, then we add the crystal at a specific temperature, and then we quench the glass, and then we anneal. So in this process, we need to balance the survival and the dispersion of the particles. So we need to optimize at what temperature we are going to add the crystal, so we don't have a corrosion, so they don't remelt. They don't melt in the glass batch, and then the time that we should wait before quenching. So if it's too long, then you have a risk of melting the crystal in the glass, and if it's too short, then you have no dispersion of the particles. And The reason we are working on that, it's because we want to do some optical battery. So a few years ago, there was this very nice paper on near-infrared rechargeable optical battery implant. So the team worked on this crystal, upconverter crystal, and they mixed them with persistent luminescent particle. So persistent luminescence is when you have the luminescence after stopping the radiation source. So by doing this upconverter, so this blue upconverter with the green persistent luminescent particles, then you can actually do in situ some photodynamic therapy. So what is happening is when you inject them in rats, you use the 980 nanometer excitation. So this is absorbed by the ytterbium. Ytterbium is giving the energy to the thulium. Thulium emits this green light, this blue light, sorry. The blue light will be absorbed by the persistent luminescent particle, will actually charge or trap the electrons. As soon as you stop the radiation with the 980, then you lead to this green persistent luminescence, and this leads to this photodynamic therapy. So we wanted to check, can we actually do the same in a bioactive glass using ytterbium and thulium in glass, and then add the crystal in the glass melt. So can the blue upconversion from the glass be strong enough to actually excite the green persistent luminescent crystal? So this is the way we did the glass, and then you have here the blue upconversion. The first step was to optimize the ytterbium and the thulium ratio in the normal glass. So here you have, so we excited at 980 nanometer, and we look at the blue upconversion, and we have the typical blue and red emission from the thulium, and this confirmed the energy transfer from ytterbium to thulium using this principle. Then we measure the dependence of the blue emission as a function of the pump power, and then we find that the slope is about 3, so we have a 3-photon process responsible for the blue emission. You have here the intensity of the emission, of the blue emission, as a function of the thulium and the ytterbium concentration. So the high concentration of thulium, so in the 3 type of glasses that we did, decrease the intensity of the blue emission due to the concentration quenching. But when you increase the ytterbium concentration, so from 1 to 3 mole%, then you have a higher blue upconversion. It's because you have a higher larger absorption coefficient at 980 nanometer by the ytterbium ions. And so we also measure the emission spectra using this 791 nanometer pumping. And then, so we have the typical emission from the thulium, but we got also an emission at 1 micron. And this is due to the emission from ytterbium, so confirming the energy transfer from ytterbium to thulium in the glasses. So we try to do this glass ceramic, so using the 2-step heat treatment as we did in the past. And here is the transmittance of the glasses. So the 2 extreme glasses, so the glasses prepared with 1 and 3 mole% of ytterbium. And we have a decrease in the transmittance. The glasses become translucent after heat treatment with no sign of surface crystallization, and the lower transmittance is due to the partial crystallization of the glass. We used XRD to try to understand what's going on. So at first we did the heat treatment at TG plus 20 for 17 hours and then TP for 1 hour, and the XRDs are in black here. We do have, for low concentration of the rare earth ions, we have this calcium fluoride crystal, as we did in the erbium dop glasses. But when we increase the concentration of ytterbium, then we have some other crystal growing. So we had to reduce the growth temperature to 390 to actually only grow this calcium fluoride crystal in the glasses. And using the Scherer equation, we found that we have a small increase in the crystallite size from 16 to 24 nanometer in when we increase the concentration of ytterbium from 1 to 3 mol%. So we use a TEM, so the transmission electronic microscope, to look at the crystal. So here's the picture of what we found, and we confirm that it's calcium fluoride crystal, and we probably have some ytterbium and thulium in this crystal. So here the normalized upconversion spectra when we use a 980 nanometer, and here you have the emission spectra when we use the excitation at 791. So when we excite ytterbium and when we excite thulium. And you can see that we have sharp peaks appearing in the emission band, so like here and here. So that tend to confirm that the ytterbium and the thulium are located in the calcium fluoride crystal, as we saw for the erbium. So we measure the intensity of the blue emission as a function of the thulium, so before and after heat treatment. And when we have low concentration of ytterbium, we have an increase of the intensity after heat treatment for all the classes. And this is due to the presence of the rare earth ions in the calcium fluoride crystal. However, in the YB2, so the glasses prepared with 2 and 3 mol% of ytterbium oxide, we have a decrease in intensity of the blue emission. So even if we have the rare earth going inside the calcium fluoride, we probably have too many of ytterbium ions, and this leads to reverse energy transfer from thulium to ytterbium, and then leading to a decrease in the intensity of the blue upconversion. Nonetheless, if we compare the intensity here of the three glasses, the glass prepared with 3 mol% of ytterbium and 0.025, 0.05 concentration mol% of thulium has high intensity of the blue upconversion, and it's quite a promising material for optical battery. So what we did is we added the persistent luminescent with this composition in this glass. So the YB3 thulium 0.025, and we added 0.5 weight% of the crystal in the glass. So we use different doping temperature. So here's the picture of the glasses of what we call the composite now. When we added the particles, the persistent luminescent particle at 875 to 950 degrees C, so this is the melting temperature. And so this is the picture of the glasses in daylight and after stopping the UV irradiation. So as you can see, we have this green persistent luminescence after UV irradiation, confirming the survival of the persistent luminescent particles. But as the doping temperature increased from 875 to 950, we have less intense green persistent or afterglow luminescence from the glasses, and this is due to the corrosion of the persistent luminescent particle I was speaking about. So the larger the temperature, then there is more risk for the particles to be corroded by the glass patch, and then the melting of the persistent luminescence in the glass. In the same time, what we realize is when you increase the doping temperature, you reduce actually the intensity of the green, of the blue upconversion. And this is due to the evaporation of fluorine. So it's you add some time, and then in the glass preparation, because we were melting the glasses after 3 minutes at this temperature. So it was 5 minutes of melting plus 3 minutes of when we added the particles to get a homogeneous dispersion of the persistent luminescence. And this leads to evaporation of fluorine, and so decrease in the blue upconversion. So we had to change the way we prepared the glasses. So we actually melted the glasses at 1000 degrees C, and we added the persistent luminescence right before the quenching. So we could reduce the time, the fabrication time for the glass. And we had to work on how to disperse the particles, so it was some manual mixing of the batch. And then you can see that we have a very strong persistent luminescence, even if we use a high temperature, and uniform persistent luminescence, so we know how to disperse the particles. And because of the shorter time, shorter preparation time, then we have a high intensity of the blue upconversion. And then we pump the glass at 980, and so to have this blue upconversion and then to charge the persistent luminescence. And here is the persistent luminescent particle of the glasses when we pump for 5 minutes with 980, and then we have this persistent luminescence. And we could confirm that the blue upconversion is strong enough to charge the persistent luminescent particle. So let me conclude. Oops, if I can. Yes. So what I tried to show you today is the current research that we do on the development of new photonic glass-based material. I hope I convince you that not all of the glasses can be drawn into fibers, but when you tailor the glass composition and the spectroscopic properties, you can actually draw some biophotonic fibers, and you can monitor in situ through the changes in the spectroscopic properties of the fiber, the dissolution and the bioresponse of the fiber inside the human body. So not all the glasses exhibit this bulk precipitation of rare earth doped crystal after heat treatment. So that's why it's important to continue to work on the direct doping process to add in the glass crystal with specific crystalline phase and doping level. And if you mix persistent luminescence and upconverter crystal, then you can use some. You can develop some new optical batteries, and this could be used, as I said, for solar cell or for biomedical application, for example. So before I finish, I would like to thank, of course, my group. So here is just some small of them, some of the students. This picture was taken last week, but most of the work we have done with former students. So I would like to acknowledge them. Of course, the collaborators. So this research was done with teams all around the world. So Italy, France, Germany, Romania, USA, and Japan. And of course, let's not forget the funding agencies. So, the work on these biophotonic fibers was sponsored by this European Union Horizon 2020 Research and Innovation Program, and the Marie Curie Co-Fund Action Multiplied. But of course, we have funding from the Academy of Finland, so it's the Finnish funding agencies, and we have also some Finnish private foundations. So with that, I would like to thank you for your attention. And if you see some overlap and you're looking with your research and you're looking for new collaborators, feel free to contact me. You have here my my email address, and we are always looking for new partners. Thank you.
Thank you, Professor Laetitia, for this excellent talk. It is exactly on time, I think. And now the topic is open for discussions. I hope there will be a lot of interest from the audience.
So I'm sorry, I was disturbed at some point with your time telling me I had only 5 minutes, so I'm sorry.
Oh. Yeah.
Hello.
Jean, I see that you raise your hand.
Hello. Yeah, nice to see you.
Very nice seeing you.
Yeah, thanks for your presentation and accepting to present today. So just so you chose this phosphate glass composition. So is it because of its biodegradability of the glass? So is that a good thing in the optical battery application?
Yes. So I didn't have time too much to speak about that, but now we are working with some new partners in the US and in Spain to actually do scaffold from these glasses. So it's dispersed material. So we could load the scaffold with a photosensitive molecule or photosensitive drugs, and then place them in the body and use this near-infrared light to actually photocleave them inside the body. So yes, we need to have this reactive glass, so it can actually attach, form, or rebuild a bone while releasing drugs.
Thank you.
Any other questions? Okay, I have one. I'm quite new to this field, and where do you use exactly these optical batteries inside? Okay, you have shown one example. And are there any other? I mean,
Inside the body?
Yeah.
Okay.
Yeah.
I hope my partner will not be mad at me, but we just submitted a proposal to EU to place the scaffold actually in the brain, or not in the brain, in the bone of the brain, to detect or to release drugs which could actually stop epilepsy. So with some partners, we have electrodes which could detect, the brain activities. And when the brain starts to be crazy, then we shine the head. The light goes through the bone and then activate the scaffold, which release the drug to stop the epilepsy. So this could be actually one application that we are now working on. The other application will be for the jaw. When you have a tooth implant, there is a huge risk of having infection. So it will be just underneath the implant. So when the dentist put the screw, then you can have this biophotonic layer at the surface of the implant, and then you can shine through the jaw, because it's no deep tissue application, so the light can easily go to the scaffold and release the drug. So these are the two applications that actually we are targeting right now.
Is it like you switch this battery on and off whenever you need it? And
yes, exactly, when you need.
And
exactly.
how long will it last? I mean, degradation.
So,
yeah, I shown some examples, but what is the reasonable time? Duration.
Yes.
Where we can use it.
So here, when we do it this way, we have the persistent luminescence only for 5 minutes. But this is just the first time that we were doing the composite. So now we know that adding the persistent luminescence using the direct doping method is probably not the best way to do. And this is just to make a bulk. If we switch to scaffold, then the process is completely different. So we can add a larger amount of the persistent luminescence in the scaffold. And so we hope to reach at least 2 hours. So this is our target.
The scaffold, what is the typical structure for the scaffold? Is it like a micron?
The scaffold are actually 3D printed, yeah. And we target about 5 millimeters. So it's some kind of cube, or not cube, rectangular. So 5 millimeter for 5 by 5, and by probably 1 centimeter for the height. Okay. So this is what for us to be able to do the proof of concept. For the moment, we don't have the funding, so we are waiting for the funding to come to have some animal testing, and we will go to rabbits. So this will be more or less the target for the rabbits. size, but then you just need to scale up.
The reason why I asked about this scaffolding is that we are now trying to use two-photon or multi-photon polymerization technique and use a femtosecond laser to make these scaffolds, maybe in the same dimension as you said, and trying to grow cells in it for transplant and things like that. I was thinking maybe it is something very similar.
Okay, yeah. So my group, we are more focused on this photonic than the bio. So my partner is doing the bio, but we have some joint PhD, so doing this biophotonics. So so hopefully soon we will have. We have already some papers ongoing with the growth of the cells at the surface of the scaffold.
Thank you. There any more questions? Okay. If not, let's thank Dr. Letitia. And thank you very much for an excellent topic and excellent talk for the last almost an hour now. Okay, thank you very much.
My pleasure. Thank you.
Okay. Our next speaker is Professor ML Chidambo from Rhodes University in South Africa. I hope Professor Chidambo is online. Oh, yes. Okay. Welcome to the conference, Professor Chidambo. Maybe you are muted. Hello, your mic is muted. Hello, Professor Chidambo, your mic is muted. Okay, thank you.
Hello, is that better?
Yeah. Okay, we can hear you now. Okay, let me just introduce you to the audience. Professor Chidambo is our next speaker. He is giving us the first invited speech of this afternoon. He will speak on procedures and analysis of phototransferred thermoluminescence. Professor Chidambo is professor in physics and head of the Department of Physics at Rhodes University in South Africa. He is an author of the title An Introduction to Time-Resolved Optically Stimulated Luminescence, published by Morgan and Claypool Publishers. His research interests are on the study of point defects in materials using luminescence methods, particularly using time-resolved optical stimulation. His other interests include thermoluminescence, phototransferred thermoluminescence, radioluminescence, and positron annihilation of natural minerals and synthetic materials. A warm welcome to you, sir. On behalf of those who are assembled here, over to you, Professor Chidambo. Thank you.
Okay, thank you very much. I assume you can see my screen?
Yes, your screen is on.
Okay. Yeah, first of all, let me thank the organizers for inviting me to present this talk. It's an honor, and I am gratified. So this morning, which is your afternoon, I assume, I'm going to talk about procedures and analysis of phototransferred thermoluminescence. So it's basically a method for transporting or transferring electrons between point defects using light. So I'm going to first of all start by looking at the principles of phototransferred thermoluminescence, or PTTL. And then I'll give some examples as a way of demonstrating the process. Then we're going to look at what we call time response profiles. That is the dependence of the intensity of the phototransferred thermoluminescence on duration of illumination. Then we're also going to look at competition effects between point defects. And there's also some interest in how one can analyze for phototransfer. Then I'm going to just touch on the influence of Hall traps on the phototransfer. So what is phototransferred thermoluminescence? Well, a simplest definition would be that phototransferred thermoluminescence is thermoluminescence that is produced owing to the transfer of electrons by light from one electron trap, which is stable, to another one, which is shallow and empty. So basically, you have two types of electron traps in this type of definition. You have a source and you have an acceptor. To start with, the acceptor then will be depleted or empty. So what you are doing is you are using light to transfer electrons from the deeper one to the shallower one. This type of definition, obviously, it's a little bit simplistic. It's a tutorial definition, but it's helpful in a way so that we understand what's going on. So it's only also strictly accurate if you are the processes that you're talking about are actually done above room temperature. So if you go below room temperature, cryogenic temperatures, then the definition is not strictly accurate. Also, this implies a one-way transfer process, okay, from the deeper one to the acceptor one. But experiments show that this type of process is in fact an exception, sort of an exception to the rule. But as I said, this is a tutorial definition, and let's just leave it at that. So the reality is that deeper electron traps, sometimes they double up as both acceptors and donors. So an acceptor would be a shallow electron trap to which electrons are transferred, while a donor would then be your source. So in principle, the number of donor electron traps is unknown. You don't know it. And phototransfer also appears only at specific peaks. Okay, it's quite rare to have phototransfer appear at all peaks. Then also phototransfer appears only when you have a certain number of peaks removed. Okay, if you think back to the definition, it would imply that once you remove a peak, you can do a phototransfer and actually it will appear at that particular electron trap, but that doesn't always occur. And then the notion of source and acceptor traps is improper for some materials. Also, this talk of isolated donor and acceptor traps, it seems to imply that you have point defects that are isolated. But in fact, this notion of isolated point defects is a little bit problematic, okay? Because you always have point defects as aggregates. And in fact, in a recent paper, in 2021 by P.D. Townsend, he went as far as saying point defects don't exist. Okay. Now, also the influence of Hall traps on PDTL is something that should be considered. So in this slide, what I'm trying to do by giving all these facts is to sort of state that the ideal doesn't always occur, although the ideal is useful when explaining a process. Okay. So in this talk, then, the question is, how can one get rid of the academic notion, or how can one dispense with the academic notion and analyze systems of acceptors and donors that you actually get in reality? Okay, so we'll try and answer that question in this presentation. The measurement procedure is that, first of all, you have a sample, you irradiate that sample, and then you preheat it. So the preheating removes a number of glow peaks. Once you have done that, you expose the sample to light. And by exposing the sample to light, what you're doing is you are inducing transfer of charge from deeper to shallower electron traps. And now you then measure a glow curve, and during the measurement of the glow curve, that's the step where you then monitor the phototransfer or the phototransferred thermoluminescence. So here below is a graph that sort of explains the process. Okay, so this is a temperature time sketch. You start with irradiation. This here is the preheating process. The sample is then cooled back to room temperature. And in this at this time, then you illuminate your sample, you expose it to light, and then you heat it again to high temperature. And it is during this stage that you then monitor the phototransfer. Okay. So let me give some examples. The first example I want to give is tanzanite. Tanzanite is a gemstone, a very, very rare gemstone, which shows 4 peaks in its glow curve. So this is an example of a glow curve of tanzanite. As you can see, the peaks are not, well, we can see 3, but they are actually 4. So we have a very high intensity peak and others that don't actually stand out that much. Okay. This sketch, this graph compares a glow curve measured without any preheating, which is the first one here. And then the one in red is measured after preheating. Okay. So once you've preheated your sample, you can see that you've removed peak 1. Okay. And then in the third stage of the process, you expose the sample to light and then measure your glow curve again. So this one in blue is measured after exposing the sample to light. And we can see that the first peak, or peak 1, is regenerated. So this is your phototransfer. In other words, the electrons that are responsible for that emission have been transferred from some deeper electron trap to this shallower electron trap. Okay. Here's another example of aluminum oxide doped with carbon and magnesium. This one is a little bit complex because it's got a huge number of peaks in its glow curve. Okay, this dark line here. Okay. Then this curve with open symbols is measured after preheating to 60 degrees and exposure to light for 10 seconds. So the preheating removes the first peak, and a 10 seconds light exposure regenerates the first peak. Okay, so it's an example from aluminum oxide. Okay. The question is, how does one analyze phototransfer? Okay. So the motivation for this study is to try and develop a formalism for analyzing phototransfer. Okay. And in that formalism, we want to actually develop or analyze photo transfer as a system of acceptor and multiple donors. Okay. We don't want to use assumptions. We don't want to use guesswork. We want everything to be based on empirical models. Okay. So going back to the case of tanzanite, okay, how do we identify which ones are acceptors and which ones are donors? Okay. So you can do that using this process. If you irradiate a sample and then you preheat it, then after each preheating, you expose it to light. Okay. Then you change, you irradiate the sample again, change the preheating temperature, expose it to light again, and then keep repeating this process in 10 until you have actually removed all the peaks that appear in your glow curve. Okay, it's a time-consuming process. It's a very long process, but it gives useful information. So here is a result from tanzanite. The x-axis shows the intensity. The y-axis shows the preheating temperature. Okay, so I've got plots here for peak 1, peak 2, and peak 3 that I showed earlier. We can see that peak 1 here, it drops, becomes stable, then drops again. Okay, peak 2, again, a little bit stable to start with, then drops in intensity, then becomes more or less stable. A peak 3 grows in intensity, then decreases again. Okay. So the decrease of peak 1 and the decrease of peak 2 between 120 and 500 degrees, they seem to be concomitant. And in this area here where I've circled, you can see that as peak 2 decreases in intensity, or as if it's removed by preheating, the intensity of peak 1 also drops. Okay. Peak 3, the higher temperature peak, it becomes more intense with preheating and then decreases. Okay. So we can guess here that peak 3 acts as a competitor for charge released from the electron trap for peak 2. Okay, because the fact that peak 1 is becoming weaker and weaker as peak 2 becomes weaker and weaker, it implies that the electron trap of peak 2 is actually the donor for peak 1. Okay, but these preheating temperatures here should not affect the electron trap for peak 3. So peak 3 should in fact be stable. It shouldn't decrease, it shouldn't increase, it should just be stable. But we can see that its intensity actually increases, which means that that electron trap acts as a competitor for charge released from the electron trap for peak 2. Okay. So this summarizes what I've just said. Okay, the source of phototransfer at peak 1 is electron trap for peak 2, and the main donor, once peak 2 has been removed, the main donor becomes the electron trap for peak 3. So these are like qualitative conclusions we draw from the experimental results. Okay. Now, remember at first I said you want to actually analyze the phototransfer as a system of an acceptor and donor. Okay. So we can't say that the phototransfer in tanzanite can be regarded as a system of one acceptor and 2 nominal donors. But the contribution of those nominal donors actually depends on the preheating temperature. Okay. And that was demonstrated in my last graph. Okay. So this will give us a means or information to analyze the time response profiles or the dependence of PTL intensity on duration of illumination. Okay. So here are measurements, experimental results. You have PTTL intensity versus duration of illumination. And we can see that peak 1, it simply decreases, as does peak 2. Okay, the intensity of peak 3 goes up a little bit, then becomes, it continues to decrease. And this is measured over 5,000 seconds. Once you have removed peak 2, we can see that the intensity of peak 1 goes up a little bit, then decreases. The number of donors for peak 1 here is we can see that it's actually 2. Okay, and the number of donors here is just 1, since peak 2 is removed. Okay, again, let me emphasize that these are qualitative conclusions. Okay, now the analysis. So let's consider that for a system of 1 acceptor, we have a system of 1 acceptor which we call K and N donors, and that the concentration of electrons in the acceptor electron trap is NK. Electrons, concentration of electrons in the donor is N of N. Okay. Then as we illuminate our sample, electrons are stimulated from a donor at a rate F, which is phi multiplied by sigma, and phi is the incident photon flux, and sigma is the photoionization cross section. Okay. Now, once electrons have been removed from a donor, okay, or from a point defect to the conduction band, only a small fraction, or only a portion of them will actually end up at the acceptor electron trap. So using these facts, one can write a set of very simple first order differential equations in this way. This equation 1 shows depletion of electrons from a donor. Equation 2 shows depletion of electron from another donor. Then the third equation 3, it shows the depletion of electrons from the acceptor during illumination. This term shows the fact that you have a portion of electrons from the donor actually ending up at the acceptor. Then the third term is a portion of electrons from the other donor ending up at the acceptor. Okay. Now, a more convenient way to express something like this, because remember, you can't always know the number of donors in your sample. If you do, if a sample is well behaved, you can guess, but in reality, it's difficult. So sometimes it's more convenient to express this as a matrix. So if you have a general system of 1 acceptor and N donors, then the transfer of electrons from donors to an acceptor can be written more compactly, as I've done here in equation 4. So for a system of 1 acceptor and two donors, you can solve this system very readily. You have 3 solutions because you have 3 equations, but our interest is in the change of electrons at the acceptor, and equation 6 gives us the particular, it gives us the particular solution for that particular system. Okay, so let's see how well this then applies to tanzanite. Let's compare the model and experimental data. Okay, pick 1 after preheating to 120, 1 acceptor and 2 donors. We can see that the model actually describes the experimental data quite well. Pick 1 after preheating to 230. You have one donor, And again, you can see that the model describes the experimental data very well. This is also reflected in the residuals just above the curve there. The other point I showed is the competition effects for peak 3. Okay, where peak 3 seemed, where the electron trap for peak 3 seemed to act like a competitor. So in this case, you can write the concentration to be N3, okay, where N3 is N plus NA, and N is the number of electrons available in the conduction band. NA is the number of electrons immediately after irradiation, and NA will be a constant. Okay. The increase in signal can be expressed in that way, because this is the number that you are getting from the donor minus the number that transits to the competitive route. Okay. So the solution to that form is equation 9. But the intensity of peak 3, it initially increases with preheating, although there are no new donors. So lambda must be negligible and N is just proportional to T. Okay. And the decrease, you can express the differential equation in this way, where the first term is demonstrating the loss due to optical stimulation. The second term is the loss due to preheating. But we can assume that preheating causes the most change. Okay, so if gamma 3 is greater than F3, then you simplify the solution using Taylor series, and you get this solution here for N3. Okay, so again, if you compare the model with experimental data, you can see that the prediction of the competition effect is quite good, and also the decrease due to that occurs afterwards due to preheating is actually well predicted. Another way is if you don't know, okay, you don't know the number of donors, you don't know the number of acceptors, but you at least have a general idea, then it's possible to use vector fields, because with vector fields, you don't actually need a solution to a differential equation. Okay, so if we use a vector field model for the increasing portion and the decreasing portion, we can actually see that the prediction of the solution is that it will increase with time initially, and it should decrease initially. It should decrease later with time. Now, the vector fields, mathematically, it's a collection of solutions. So if you have one particular solution, then that solution will simply trace, it will trace a line tangential to a family of the vectors. Okay, so a vector field solution will display the general shape of the solution that you can expect, which is also quite a neat way of looking at these results. Okay, so sometimes you also want to use theoretical modeling. So instead of using first order differential equations, you actually want to include the possibility that there can be retrapping. If you do that, you can write a set of nonlinear equations like this, which you can solve using some software, maybe Mathematica or Python or whatever it is. So in this example, here is the solution of this model applied to some data from aluminum oxide. Okay, so you have three ways. You have qualitative models, you have simple first order differential equations, or you have the possibility of using theoretical modeling. But in all these cases, the models are actually based on what experimental data predicts. Then Hall traps, sometimes Hall traps cause a sudden and dramatic increase in intensity. I'm not going to say much about this, but in oxides like aluminum oxide, when holes are released, it can catalyze the formation of F+ centers. But this process would depend on Hall trap. The thing with F+ centers is that they can act as recombination centers and can also affect the intensity of your photo transfer. Okay. So there are two examples of Hall centers there. Okay, so to summarize then, photo transfer should be analyzed as a system of acceptors and donors. Okay, it shouldn't be based on guesswork. The number of donors should be determined by experiment, and theoretical assumptions are a problem, and in my opinion, we need to dispense with them because donors don't always act as such. And also when you have competition effects, you need to account for them. I've demonstrated models here, qualitative, simple first order, using matrices, using vector fields, using theoretical modeling. But as much as possible, the models that one uses or that one develops should be based on experimental evidence. And then lastly, phenomenological models, vector fields, and theoretical modeling can be used. And the nature and the role of Hall traps should be considered. Okay, thank you very much. That ends my talk.
Thank you, Professor Chidambo, for your wonderful talk. And it is, I'm sure that there will be a lot of interest, and this on the thermoluminescence from materials. Now, there is time for one or two quick questions, because we are slightly running out of time, but we still have time for one or two questions. Okay, Professor Chidambo, I have one question. Okay, you were talking about this thermoluminescence spectra, and in which range are these emissions in the electromagnetic spectrum? Is it in the visible IR?
Yes. Okay, so the examples I gave are in the UV, between like 340 and 360 nanometer. But you also get emission in the blue, say between 400 and 470. So the detection filter that you use depends on the emission band of the sample. So UV or blue.
Is it possible to engineer the spectrum by adding point defects or introducing some defects to the material? Is that the way that you do to change the variation?
Yes, it's possible. For example, in aluminum oxide, so when you dope aluminum oxide with carbon, you generate a large number of F centers, and those F centers will emit at 420 nanometer. Now, when you double dope carbon and magnesium, you still get emission at 420 nanometer, but if you anneal the sample, you force the emission to the F+ centers at 330 nanometer. So you can treat the material by doping or annealing it or heat treatment, and that will modify the emission band. Yes.
Thank you.
Just What are the typical decay times of these emissions? Are these fast emissions, or are they slow in terms of?
Well, it should be around microseconds, so which is I would say it's slow, because you can have faster processes, but from time resolved measurements, usually like in quartz and some materials, quartz is like microseconds. Then in the aluminum oxide example, it's like milliseconds. So it's sort of a slow time process. Yeah.
You also mentioned about some natural crystals as well. So do you expect them to be, without any impurities, or do you consider any presence of impurities in such crystals?
No, the natural ones will always have impurities. If it's got, well, it will usually depend on the type of impurity. If your impurity is mostly like transition metals, copper and iron and so on and so forth, we find that the emissions are quite weak. But for some type of transition metals like manganese and chromium, then you get very high emission. But natural minerals, gemstones like the ones we have studied, they always have impurities, and those impurities, they also define the point defects that act as electron traps and recombination centers. Yeah.
Thank you.
Any other questions? Oh, I have just one more question. Okay, I think we are running out of time, but still for a quick answer. I mean, when you change the temperature, the intensity of this thermoluminescence changes. Are there any ways to change the frequency or the color of the spectrum? I mean, color of the radiation by changing the temperature?
Yes, not changing. What happens is that if you can measure a spectrum if you are using a spectral detector. So your sample can emit, say, in the UV, in the blue, or say infrared at the same time. So if you are using something like a photon position detector, then you can measure a spectrum. But some systems usually use a filter, like a detection filter. So that detection filter then will only detect emission between a certain band. But during the measurement itself, usually your emission peak or the wavelength of emission will remain the same.
Okay. Yes. Thank you.
Okay.
Thank you very much for this wonderful talk and the topic that you have presented. On behalf of the organizers and myself, a very thanks for it. Thank you. Thank you very much. Okay.
Thank you. Thank you. Bye-bye.
And our next speaker is Professor Radhakrishna Prabhu. He'll be talking to us on lanthanide-based micro-nano photonic devices and their emerging smart applications. And let me introduce Professor Radhakrishna Prabhu. He is probably not a stranger to a lot of you.
Yeah.
Dr. Prabhu is a professor in smart sensors and instrumentation at Robert Gordon University, Scotland, in the UK, and he is the head of RGU's Center for Research in Energy and Environment. Then is the lead for sensors and instrumentation research group in School of Engineering. He is arduous lead for Medical Device Manufacturing Center, MDMC, being developed in Edinburgh, Scotland. And also, he was the Deputy Director of Medical Technologies, JRI, of Northern Research Partnership, UK, which coordinates research in University of Dundee, University of Aberdeen, and Robert Gordon University. Then Dr. Prabhu has BTech degree from Mahatma Gandhi University, MTech from Cochin University, and PhD from Indian Institute of Science, Bangalore. After PhD, he was a postdoctoral fellow at the University of Tampe, the Netherlands, and also at Robert Gordon University after that. He has more than 25 years of research experience in the fields of sensors and instrumentation, optical materials, surface engineering, nanocoatings, and clean technology. He has co-authored more than 160 research articles and also delivered many keynotes and invited talks in international conferences. For the past 4 years, he has been the conference chair for SPIE's conference on counterterrorism, crime fighting, forensics, and surveillance technologies, maybe a very emerging field. He has supervised his 16 PhD students to completion and currently supervising 10 research students. Also, he has collaborations all around the world, including UK, Brazil, Portugal, USA, Germany, and so on. And with that introduction, a warm welcome to Professor Radhakrishna Prabhu. Over to you.
Thank you, Riju, for a small introduction. Again, I had sent a big list, actually, don't worry. And thank you again for the organizers for inviting me for this conference. Now, without much delay, I know it's running late, I'll start my talk. So I'll be talking on lanthanide-based micro or nano photonic devices and their emerging applications. And I'll be mostly focusing on the application side than the material side. And again, lanthanides have been the backbone of optical-based or optoelectronic-based applications. And that has been going on for the last 50 or more than 60 years. So during these 50, 60 years, it has evolved from bulk to micro to nano layers. So the transition from micro to nano is happening at stage, and a lot of research is going on. But my talk mainly deals with the micro and bulk side of this application. Now, regarding the overview of my talk, I'll start with a little bit of introduction on me and Aberdeen. Then I'll touch some lanthanides and their properties. Then I'll mainly touch the currency security tag-ins and quickly touch some forensic and quantum network related applications for the lanthanides. Now, I am in Scotland. I'm in Aberdeen now. It's probably around 11:10 a.m. here. And it is location-wise, Aberdeen is around 2 hours flight from London. And previously you heard a talk from Letitia, Professor Letitia, and she is a little bit north of Aberdeen. So she's from Finland. So we are in the northern part of UK now. And again, Aberdeen is the oil capital of Europe. And this is my university, and it's a new building. And School of Engineering is located here, and my laboratories are around here. So with that small general overview, what are lanthanides? Lanthanides are also known as rarer elements, so which you already heard from Professor Letitia. And they involve mostly these 17 elements, including these lanthanides, this group 57 to 71 with atomic numbers, and this scandium, and yttrium. So overall, these 17 elements are generally called as lanthanides or rare earth elements. And they have been used in many applications like electronics and widely in lasers and optoelectronic applications. In magnetic materials, some of these lanthanides are widely used in high power magnet, making high power magnets. So from optical perspective, so this talk is mostly on the optical side. Erbium, terbium, dysprosium, neodymium, or erbium. So these are the widely used lanthanides out of the 17 for optical applications. So one of the important properties of these lanthanides is the outermost electronic shell is mostly full, while 4 of shells, inner ones, are unfilled. So that means these 4 of shells which are unfilled are screened from crystal field effect by the outer 2s or 2p base electrons. So because of this, the influence from outside or environmental influence in emission of luminescence or fluorescence is minimum because of this highly protected environment. So that's the key or important property of rare earth elements or lanthanides. So in this picture, you can see they have very sharp emissions around this. I think it's for dysprosium. You can see visible emissions from 490 to 670 as sharp emissions from dysprosium. So you have unique luminescence spectral properties, and they show strong and sharp absorption and emission. So you can see from dysprosium emission spectra, they have very sharp absorption as well as sharp emissions here. And in addition to that, these excited state lifetimes of these ions are quite long, varying from few microseconds to milliseconds. That provides additional advantage for rare earth elements or lanthanides for optical applications. One of the popular host material for these lanthanide ions is borosilicate glass or aluminosilicate glass. Again, yttrium aluminum garnet, which is well known, has been used as a host material for ND, neodymium, and this has been used for developing Nd:YAG-based solid-state lasers. Again, this is one of the Nd:YAG-based crystals. And this is, again, some of the glasses we developed in our own laboratory by doping different rare earth elements into the glass matrix of borosilicate glass. So by changing the concentration of the rare earth elements doped in the material, we can change the fluorescent or intensity of fluorescence from these glass materials. And again, based on the host and the dopant, we might have to strike a balance to get maximum fluorescence based on the doping possibility. In this case, you can see maximum doping for Pb is around 1.5 mole percentage. So lanthanides have many applications. Optical fiber-based application, especially erbium-doped optical fiber, is the backbone of optical fiber communication, which is revolutionizing now the optical communication area. So erbium-doped fibers are very important. And on the laser side, as I said earlier, Nd:YAG laser is one of the important subset of lanthanide dope or lanthanide-based lasers. Then yttrium is also another emerging laser in this area. Again, phosphors based on the lanthanides are also widely used in display as well as white light emission from LEDs. And again, there are rare earth emissions in near infrared, and they have been used for many other applications. So rare earth elements have many applications around optics or optoelectronics. Now, my talk mainly centers around currency security. All over the world, there are paper-based currencies, now probably moving into plastic-based currency. Now, how can we enhance the security of this currency? The governments, again, counterfeiting or currency security is a multi-billion industry for the government or the industry. Again, counterfeit goods are making a loss of probably 2 to 3 billion per annum for worldwide industry. So one of the interests from our group was to develop a anti-counterfeit technology based on rare earth elements or rare earth technology. So to develop a security feature which can protect the document currency. So there are a set of designs you can implement. Then you can have substrate, paper, a special quality substrate for making currency. Then you can go for special printing on the currency. So your currency can be printed using special printing process. That would be difficult to reproduce. Again, you can use different types of ink which are specific to security area, or the technology can be kept secret. Again, there are a set of OVD devices like holograms, foils, or other things that you can incorporate into the currency to enhance the quality of or enhance the security of these currency notes. Now, in Scottish banknotes, typical ones are you can have a high quality printing, you can have a set of serial numbers or one serial number for each set of currency. Then you can add fluorescent-based signatures into the currency. Then you can add hologram. These are the typical ones. Again, you can see again from the 3 or 4 Scottish banks, they have in general a watermark. Okay, and then there is a thread for different currencies. Then again, you can have see-through options inside this currency note, which will change its color as a function of viewing angle. So these are the typical security features. And each currency has multiple layers of the security features that enhances the overall security of the currency or makes it difficult to counterfeit. So as we increase, so this is another approach. This is a euro currency, where you can see a fluorescent dye has been used to print these features. So this is the white light image, while bottom are the UV image. Under UV illumination, you get different colors, and that can be used as additional security feature. And most of these dye-based fluorescent signatures are emitting or will be emitting in broad spectral bands. So that limits the number of combinations that you can use in enhancing the security. So most of these emissions are probably 100 nanometers to 60 nanometers wide in the optical spectrum. So that limits number of dyes we can use and limits the security applications. But we were looking into utilizing the sharp emissions from rare earth to enhance the security. So in that line, our application requirements were to develop a invisible security feature or invisible spectral signature that is specific to the barcode or a currency, which can be automatically authenticated in a cash vending machine typically. So it should be automated, as well as it should have invisible security feature. So for that one, we selected rare earth as one of the possible candidates. And again, other requirements were advantages from rare earths was narrow spectral emission bands. And since it has narrow spectral emission bands, we can have large number of possible permutations. Again, we can develop simple detection system, and it can be used for automation. And we want these security features very rugged. That's another requirement, because currency nodes will go through different environments. So these were the requirements. So based on that, we identified rare earth as one of the possible contenders, and based on, again, discrete emission peaks, we decided to select a set of rare earth elements. And in addition to the spectral emissions, these fluorescent emissions have long fluorescent lifetimes. That gives an additional security feature for the currency nodes compared to molecular ones. The first thing is to compare the emission spectra from a typical rare earth called dysprosium. So we tried what is the effect of solution and what is the effect of same ion in borosilicate glass. You can see this is a spectral emission in a 3D view. This is the excitation and this is the emission. And you can see in the liquid, you have more sharper emissions than in the borosilicate glass. And this absorption bands have broadened, while here in the liquid, they're much more sharper. Again, the absorption band in glass is higher than in the liquid. So one understanding is by incorporating rare earth element, we can increase the security based on this sharp absorption and emission features. So how do we manufacture, or how do we prepare the glass with rare earths in it? So we have a set of high temperature glass furnaces, which can go up to 6,600 degrees. So in this case, we selected borosilicate glass matrix as the base material, and we doped a set of rare earth elements into it. So since the borosilicate glass is used, the temperature can be around 1,200 degrees. And we used melt and quench method to fabricate the glass. You can see high temperature furnace, and this is through a filter. You can see these ingredients were mixed and put in a platinum crucible to melt the glass, and it was quenched and pellets were made. You can see it's a clear glass, and these glass are doped with rare earth elements. Now we tested the absorption spectra. You can see here, this is the blank absorption spectra of borosilicate glass, and it has a clear or nearly small absorption in the visible range. So we can use most of this visible range for our spectral applications. Again, if we dope europium in this glass matrix, you can see the characteristic absorption peaks of europium. So these are sharp absorption peaks around 470. Here you can have 385 in the near UV and around 532 around for europium. Similarly, you have for dysprosium a UV peak as well as some visible peak. For terbium, you have a visible peak around 474.88 and UV peak. So in general, we can use these rare earth elements for for generating strong absorption bands around near UV as well as in visible. So a typical spectrum from europium. You can see this is the europium glass, and this is the typical absorption spectrum from the borosilicate glass. You have the sharp absorption spectrum around 465 and a UV absorption band around 385. And again, emission spectrum is also very sharp, around peaking around 620 and a smaller one around 590. So these peaks can be used as a special signature for europium dope classes. In addition to this sharp emission, the spectral lifetime of these glasses can be of the order of millisecond to microsecond. In the case of terbium, you can see the lifetime is around 2.26 milliseconds. So that's for an excitation around 375 nanometers and emission around 545. And similarly for a dysprosium doped glass, the lifetime is around 744 microseconds. That's for 386 nanometers and emission around 575 here. So these lifetimes are specific to these rare earth elements, and that might change, or these lifetimes might change based on host matrix. So that provides an additional security feature for these elements, or security feature overall. Now, that was single dope glasses, while again we tried multi-dope glasses to enhance the combination of spectral signatures. We doped dysprosium, europium, and terbium together to form the borosilicate glass. And in the combined form, still you have this strong absorption bands of dysprosium, europium, and terbium inside the glass. So this is the typical signature from a multi-dope glass using EUTB and DY. So you can see this is the 3D excitation emission spectrum, and while this is the excitation spectrum for this multi-dope glass, it has a broad excitation around near UV, ranging from 350 to around 400, 410. And very sharp emission bands, which are specific to each of those rare earth elements doped inside. So this is for EU, this is for a DY, and this is for the TB. So you have specific emissions, which are characteristic emissions from this rare earth element. So in principle, we have developed a multi rare earth dope spectral signature in borosilicate glass. Again, we try to increase the combination or increase the spectral codes by changing the concentrations of each of these elements doped in the multi-dope glasses. So in this case, we change dysprosium to 2, then you can see this is the spectral emission associated with TB. Then we increase TB from 2 mole percentage to 2.5%, its spectral intensity increased. So by changing the concentration of each of these dopants, you can tailor the spectral intensities of the fluorescent emission. And in this case, this TB was increased. And in this case, if you compare this one with this one, you can see dysprosium emission increases in line with the concentration of. So this provides additional set of spectral codes by varying concentrations of doped elements. Now, in addition to that, these elements, multi-dope glasses, they have their own lifetime spectra based on the doped elements. Now we have developed multi-dope glasses and single-dope glasses, and in principle, they are nearly transparent. They are in the glass. And in the case of UV illumination, you can see all the glasses which are fluorescent now. And if you look at here, some of the powders we made from the glasses, and these powders were made using ball milling process. So micro particles of this glass were made using ball milling process. And these microparticles are the spectral signatures or microtagants. And these microtags were spectrally encoded inside the glass. So each microparticle has its own spectral code. Again, our objective was to make an invisible spectral code that can be embedded into a currency node. So we used a screen printing method to demonstrate this spectral integration approach. So we embedded spectral codes inside the paper as well as on top of the paper. This is a typical paper we made by screen printing onto the paper. And this was the barcode we printed. And you can see the output from a specially made detector just specific to this European tag. And you can see it has strong signals and very nearly zero background. So this provides good signal to noise ratio for the detection system. Then moving from single stage detector or single detector to multi-detector or multi-channel detector, where we used all the 3 rare earth elements, and still we have all the still we can differentiate all the rare earth elements and have the nearly zero background level and lifetime discrimination integrated into these detection systems improves the signal to noise ratio from this environment. So that's how we have done the spectral part of it. Now, then recently there was a paper from Miguel et al. And they were trying to integrate the similar luminescent properties from lanthanides into using spatial and selective excitation. So they were trying to use the imaging system or cameras. We had our own cheap detectors, while recently this team were trying to utilize cameras by using 1 laser or 3 detectors or 3 lasers in 1 detector with time-resolved excitation or time-resolved emissions to simplify the current detection method. And they were trying to integrate this in authenticating a set of products made from medical to pharmacy and distribution and shipping. So they could authenticate all the products with the help of a digital key, which is generated by the security system. Now, quickly, I'll touch on forensic application. Again, we have been working on nano rare earth doped materials, but this was taken from some other group and Wang's group, where they were trying to develop nano powders doped with rare earth elements. So one of the things in forensics is crime scene or personal identification from crime scenes. And they use powder dusting method to identify or take fingerprints from the scenes. And current powders used, they have low contrast. So they have an issue of low contrast from the current powders used. And this group was trying to develop lanthanide doped nanomaterials for using as test material. So you can see they develop EU-based and TB-based nanomaterials, and that can enhance the quality of the detection or fingerprinting. So they used these 2 EU and CE-TB-based combinations, one in green and one in red. EU is in red and TB, this one in green. So under white light or a normal full bright condition, this is the typical image. So you can see the contrast is very bad. And with this dyes, with exciting using 250 nanometers illumination, you can see it is it's giving very large contrast. Again, for the second dye or second nanoparticle powder, you can see green emission giving a very sharp or contrasting picture. And they used this type of nanomaterials, and you can see the absorption band for the red one. This is U-doped nanomaterial, which has strong absorption around 277, while for the green one, strong absorption around 262 nanometers. So exciting at this wavelength can get emission around 619 for EU and these green emissions for the TB cerium dope material. And these are the typical pictures of the nanomaterial. Now, last slide is on quantum computing. So in the future, currently, digital computers are used and use binary bits as their main storage bits. So in the future, it's going to be quantum computers, and quantum computers are or will be coming up in the scene in the next 10 to 20 years time. And counterparts for the binary bits in quantum computers are qubits, which are a bit more complex than the binary bit. They're zeros and ones. Qubits have, again, for each of these zeros and ones, you have additional spins attached to that. So with this approach, these next generation quantum computers are going to be a million times faster than the current supercomputers. So one of the bottlenecks for these quantum computers is development of these qubits. So one of the possible options, there are different platform technologies being explored at the moment for quantum computing and quantum networking. One of the possibility is lanthanide ion-based platforms. So there is a group in Caltech and some other groups in Europe and other places are working to develop lanthanide-based platforms, which can probably substitute current silicon-based platforms for the computers. So a lot of research is going on, and they are trying to demonstrate lanthanide-based qubits for memories, repeaters, and transducers. So here you have, I can see in the picture, NT-doped resonator with high quality factor. That's one of the requirements for quantum computers. They are expecting to improve the quality factor up to the 10 to the power of 6 to 10 to the power of 7 orders. So here at the moment, this is the typical quality factor for the resonator developed in the lab conditions. And this is at the very early stages of development, and they hope to develop a lanthanide-based platform for the future quantum computers. So in summary, I have shown you lanthanide-doped optical materials can be used in various optical applications. And glass-based or glass doped with lanthanides can be used as microtagants and to avoid counterfeiting or improving the currency security. Again, lanthanide doped nanoparticles have been promising. They have been used as nanopowders for forensic applications. And qubits, quantum lanthanide-based qubits can be a new platform for the next generation quantum computers. Okay, this is not just everything my work. There are a group of people who have been working on this. So these are my collaborators or whom I have worked with previously. Thank you very much. Any questions?
Okay, thank you, Prabhu. It was thank you for explaining or reminding the versatile applicability of lanthanides, our security, computing, forensics, and many more. Okay, yeah, we have time for a few questions. Questions?
Shall I ask something?
Yeah, go ahead.
Yeah. Hi. Thank you, Dr. Prabhu, for that very kind of presentation covering a large number of applications or areas, and it's going to help us for in terms of my presentation. So, in terms of its applications in counterfeiting, has it been used in other areas than the banknotes because you can actually print it for many other applications as well.
One of the challenges for requirements for quantum, currency security is it has to be a rugged design. So the environment should not interact. And once the security signature is made, it has to survive for probably 100 years. So there's a ruggedness. So in this process, through our process, that's why we went with the high temperature glass forming. So we started with bottom to top approach, went up to glass, then broke it down to bottom, came down to top to bottom process for printing application. So idea is to develop an ink and that can be printed using desk-jet printers. And so through this process, we wanted a probably micro particle of probably 10 micron to 20 micron in size, So that was a requirement for printing. So we could bring down the particle size to 10 micron and around for printing application in this case. So, and in this, because we have gone through the high temperature process, the spectral signature remains intact. And we are using a micro tag than nano tag. So the surface to volume ratio is slightly different in this case. So the spectral signature remains intact, even if you put this currency note in liquid or solution or in acids. So you have a rugged, so that was, if we move on to the nano side where these developments are coming up, the susceptibility might be a bit more unless we encapsulate into a different package. So that's the one possibility. So so if we look at the layer by layer deposition, which is required for quantum computers or the resonators, where you want to add each ND ion in an appropriate position, that might be challenging and might be susceptible. That's my view, because it's in the early stages of development. And it's overall, it's the 700 nanometers waveguide or resonator width. So it might be susceptible to environment. So from security side, we want a rugged one, but from the computing side, we want high Q. These are the requirements, but they are trying to increase the high Q in the later stages. That's a practical challenge. And it might take some time. That's all I can say now. This is the early, but there's a potential for lanthanide-based glasses or lanthanide-based platforms in and around quantum computing. But other technologies are also there. This is one of the possibilities.
Thank you.
Okay. Any other questions? Okay, if not, let's thank Professor Prabhu again. And thank you very much for this wonderful talk. Thank you.
Yeah, Riju, there are many questions coming up in the chat box.
Okay.
Yeah, I know. I'll answer them, but you carry on with the next talk.
Yeah, I think it's
already delayed. You carry on. I'll answer them. Yeah, okay. Thank you very much, Riju. Okay. Bye, Jin. So you have a talk now, right?
Yeah. Next is Jin.
Yeah.
Okay. Yeah. Plus, probably I just want to apologize. Previously, you raised your hand for Professor Letitia, but
that's fine. You know it. Yeah.
Yeah. So please email her if you are. Yeah.
Okay. Thank you.
Bye. Oh, sorry, I haven't also. Then our next speaker is Professor Jin Jos from the University of Leeds, UK, who is going to guide us through the femtosecond laser-induced plasma manufacturing of functional materials. And as the chair of this conference, you probably know him. Professor Jos is the inventor of ultrafast laser plasma doping process that has been the core technology behind novel optoelectronic applications that he currently develops. I think we'll speak about, we'll talk here about that. And he took his MSc and PhD degrees in physics from University of Calicut and Mahatma Gandhi University respectively. Then after PhD, he was a research fellow at the Polytechnic of Milan, Italy during 2001 and 2002. He joined the Department of Physics, IIT Guwahati, and was a senior lecturer and assistant professor until 2007. In 2007, he joined School of Chemical and Process Engineering in the University of Leeds, UK, as a senior research fellow and project manager, and where he's a professor since 2013 and chair in fundamental materials. And his research interests are in the areas of photonic glasses, femtosecond pulse laser deposition, and plasma implantation, planar waveguide devices on glass, silicon, and polymer platforms, and photonic biosensors. Then also on the functionalizing glasses and semiconductors using ULPD for non-invasive biosensing, integrated photonics and anti-counterfeiting printing in glass bottles and toughening of glass for displays and so on. Then another direction of research is the manufacturing and application of upconversion nanoparticles, materials for passive radiative cooling and laser deposition of oxide and chalcogenic materials. And with that introduction, let me welcome Professor Jin Jos for his talk. Thank you.
Thank you, Professor Joyce, for that introduction. Yeah, it was a bit longer than I thought. So, so yeah, thanks everyone. Thanks for joining this conference, and it's my role now to present my research at this conference. So we have heard a lot about femtosecond lasers, rare-earth materials, glasses. So I got a bit of everything in this presentation and hope it makes sense to you all. So I'm based at the University of Leeds in the School of Chemical and Process Engineering. Leeds is kind of around 200 miles north of London here. So that's the island of United Kingdom, and got England here and Scotland here, and Professor Prabhu is from here in Aberdeen. So that's where I am now. So we have heard a lot about femtosecond lasers. So we also call them as ultra short pulse lasers or ultra fast lasers. It simply means that these lasers can produce light pulses of very short duration of about 10 to the power minus 15 seconds. So that's the duration of each pulse. And that's what we usually call 1 femtosecond. So the lasers can be from a few femtoseconds to up to a picosecond. That's generally what we call the femtosecond pulse lasers. And then we have the pulse to pulse distance. So that's essentially what we describe using the repetition rate. So the lasers can be of several repetition rates. So you can have a single pulse lasers, or you can have several megahertz lasers these days. So we discuss some of the interactions of lasers with material in the previous talk in the morning with Professor Reggie Philip introducing about the different ways of producing it and different types of interaction, including the nonlinear interaction of it. And the one regime in which we are working on is about basically the intense field effect. That's where you actually modify the you change the chemical composition of the material, or you literally evaporate the material using this intense laser field of these lasers. So this is typically coming from some of these definitions around average power, peak power. So if you look at a laser which has got an average power, it's calculated using its energy per pulse into its repetition rate. It's around 1 watt, but that same laser, you got peak power, that's the power per each pulse is around 10 gigawatt. So if you focus this particular laser down, say for example, a millimeter square focal spot, then you're getting huge power, which is 10 to the power 19 watts per meter square. So we define another quantity in this materials processing, which is the fluence, which is the same, the quantity that Professor Sajjan also was describing to you in his presentation. And if you consider this intensity with the sunlight we are getting at the surface of the Earth, it's huge. We are only getting a kilowatt per meter square, but from this laser, you can produce several watts or several kilowatts of power per unit square. So that's what we essentially use. The lasers can be of different wavelengths, could be of most commonly used one, it's 800 nanometer because it was produced using the titanium sapphire laser crystal. And then nowadays it's most common is 30 nanometer, which is using the ytterbium-based fiber and crystal lasers. So we have discussed about linear and nonlinear interaction. So here again, we have a quick recap of that in terms of why we are using heat materials processing. So you can have a simple radiation which interacting with the material, then it could transmit to the material. For example, if you send white light through glass, it transmits, part of it getting transmitted, part of it gets absorbed in the material, and part of it is lost as scattering. So these are all linear interaction processes. The intensities of the lights are like moderate, so that won't make any changes to the material itself. So in terms of using highly intense laser pulses like the femtosecond based laser pulses, the laser, it has been essentially what we have is when you say very high power per pulse, the peak power per pulse means that a large number of photons are present in each pulse. So that makes new effects in the material. So you effectively exciting the materials with a large number of laser pulses that essentially, if you remember the discussion in the morning, creating a high electric field in the material with highly oscillatory electric field in the material, which can cause several kind of after effects within the material, which indeed in turn leads to very large concentration of electron density in the focused area. So when the electron density is of the order of 10 to the power 21 centimeter cube, then we believe that the material can effectively ablate on the surface. It cannot stay anymore. It expands the material, and what you call the ablation happens, and the material is basically breaking down. So it's a very short process because the pulse is of very short duration. So there is not enough time for actually the heat produced at the focal spot to dissipate into the material. So before that heat dissipation happens, it actually evaporates the material or ablates the material from the surface. So that's what we call the why it is also called the cold process, the ablation process using femtosecond laser. So this is a simple description. We have had this discussion. So how these electrons are produced within the focus material. So in a normal material, you have to excite the material with an energy which is greater than the band gap of the energy, so that the electron in the ground state can be excited, and it can be removed from the atom. So, but in a femtosecond laser process in which there is a large number of photons are involved, we can induce what we call the multi-photon absorption process. That means the photons getting absorbed in a cascaded effect, so that it effectively crosses the band gap, and the electrons can get free from the metal or from the material that is being absorbed. So this is essentially most of the experiment that I described here is happening in dielectrics. Yeah, in an electron in a metallic material, you can have the direct excitation or removal of electron. So here in a dielectric material, this multi-photon absorption is one important aspect. You can also have impurities in such materials, which can also produce direct ionization as well. So there's it's essentially the production of electrons by the excitation process in an intense pulse, which leads to the ablation of the material from the surface of a dielectric material. So in addition to the multi-photon ionization, it's also being discussed that there is a tunnel ionization process. That means the electrons can directly be kicked out of its internal from a lower electronic orbital of the atom. So there is still a lot of discussions around how exactly the process is happening. So it's still an area of research. So it's one school of thought is it's like you got an avalanche process in which the electron density reaches this level of 10 to the power 23 electrons per centimeter cube. That leads to the ablation of the material. So in short, he can describe the ablation mechanism in steps. So you have the acceleration of seed electrons, the laser field by inverse stratum absorption, basically equal to the free carrier and electron absorption. And then is a generation of secondary electrons by collision. So these already produced few electrons, then by collision creates more electrons and then leads to the ionization. And then there is this process of electron phonon coupling, that is energy from the electrons can be transferred onto the lattice. So that will also lead to the breaking down of the lattice, and which ultimately leads to the melting, vaporization, plasma formation, and or what you call generally ablation, laser ablation of the material. So this is a simple schematic of what we do. So what we have is a target material in most of my experiments. What we use is a kind of rare doped glasses. So these glasses, when you excite using a laser, the laser being absorbed, the laser, what I said is a femtosecond laser. Because of its unique characteristics, it ablates the material and it's getting deposited on a substrate. So this is similar to any laser, pulse laser deposition process. So you can use different types of lasers for pulse laser deposition, for example, nanosecond lasers, which are of higher energy per pulse, but will be in the wavelength of, say, UV, which are called the excimer lasers. So those lasers usually, ionize the material. And then you have nanosecond lasers like in the longer wavelengths, which can also be used for ablation of materials like Nd:YAG lasers. But in this case, we are discussing mostly about the use of femtosecond lasers for this ablation and deposition-induced processes. So one critical difference between ablation or using a UV excimer laser or femtosecond laser in a dielectric material like glass is most of the ablated materials contain nanoparticles than ions. So that means the films that you grow using the femtosecond lasers can structurally be very likely be different from that of that deposited using say an excimer or UV nanosecond laser. So here is a simple example of how it happens in real time. So you have a laser interacting with the material, you're creating ions and nanoparticles of the target materials, it's getting deposited in the material. So that's what we call the pulse laser deposition. So the process that I described here is slightly different in the first part of the talk, in which the deposited materials are actually getting diffused into the glass or docked into the glass material, so that you essentially change the composition of the substrate, what you call here, by the incoming material ablated using this femtosecond laser. So this is a simple video of what happens when the laser is focused and scanned over the surface. So that's the kind of target glass I was mentioning. So you can see here, maybe I get my pointer. So you see that's the glass here, and if I start the laser, so if I start the laser, you can see that it's being scanned. So you see the points where it's mostly getting ablated. So the laser got a certain, so this is run with a certain repetition rate or simply frequency record. So you scan the laser, it is optically scanned. across the substrate, target, so that it's uniformly ablated. So if you focus on one point, it ablates from there, and it's basically you drill a hole in there. So you want to continuously ablate smoothly across. So you have to move the target across the laser beam, and also you have to move the laser beam in the other direction. Scan the laser beam in the perpendicular direction. So you need to get a uniform ablation of the substrate, and then you have this target, and you have the substrate over it where it's getting deposited. So you can increase the repetition rate of the laser, so you can get a kind of or nearly continuous plasma plume from the ablated from the target. So that white spot is where the laser is focused, what you see there. So it's a simple video of showing how the material is getting absorbed. So this is some idea around what happens at different time scales of the different time scales from the plasma when it expands. So you see that initially you can see a central point of the plasma, and then it's getting expanded, and then it's getting more. So what we here see is a scaling with time and signal. So initially you produce the ions and atoms. So that's in the sort of femtoseconds to nanosecond time range. And then you have basically the nanoparticles coming out, and then the droplets coming out, say nanoparticles in the up to 5 microseconds, and around 10 microseconds, you see the droplets coming out. So we need to really control the process so that we can reduce the droplets to a minimum, and we increase the nanoparticle concentration to a maximum, so that you can get a more homogeneous film at the substrate. So this is from this reference. So it's showing the effect of the ablation from the different surfaces like titanium, silicon, and aluminum nitride targets at a given fluence. So you can see that, so it's material dependent, and at the same time, you need to control the fluence as well for each material to get the uniform distribution. But in each case, you see this is more deposited as particles. Yeah. So the particles dimensions will also be, or it will also form clusters. So you need to control the fluence, the laser energy per unit area at the target in order to get a uniform ablation. So that's the first step in optimizing the laser deposition process. And what we do is we can do it a trial run to see what's the best number of pulses and the fluences for the best uniform ablation. So this is the procedure that we used, which is described in this paper for ablating a tellurite-based glass, which is used for photonic applications, and which can be doped with rare earth ions, and then we can use it as a source of rare earth ions to put it into the into a silicate surface. So here you see the different fluences. You see the ablation spot, how it looks like when the laser hits at the surface. So if you see the point, the spot here at D, you see a more uniform ablation of the target material, and we try to use that fluence. So based on the number of pulses, you can find out what fluence we want to use. So that's the fluence that we want to use, or around that energy, the fluence that we run the experiment. So it could be, if it's number of pulses per site is different, you will have a different fluence that you want to use as well. So another way of looking at it is you look at ablate and deposited materials and see how the particle size is distributed at the surface. So this can be done with a simple experiment. You do a very short deposition so that there is no multiple particles coming up. So you get this, then you look at the substrate, and then at different fluences, and then look at the particle size distribution at the substrate to see what's the best fluence to go for. So here you see this is the fluence for A is like 0.2 joules per centimeter square. So that's the lowest. So you see now some particles at the surface, but it's not fully covered. So there may be smaller particles which you cannot see in the this SEM image, the scanning electron microscopy image as well. So as you increase the fluence, you have more particles, and you will also see larger and larger clusters forming, or larger particles coming up as well, which is correlating to the result I have shown there. Maybe droplets coming out of the target. So that's the basic optimization. So you find out the best fluence for uniform or homogeneous distribution of particles at the substrate, and also looking at the best ablation of fluence for the uniform ablation of materials from the target. So this is a calculation based on that image to see how the particles are distributed at the surface of the substrate. So in this case, you see it's around 20 nanometer is average particle size that you produce. So now we look at the typical deposition process. I said the material will be ablated and deposited on a substrate. But here what we are looking at is the ablated materials to get into the substrate, so that you basically modify the substrate layer by layer deeper into the substrate. By modifying, you mean that we can change the refractive index of the material, and we can also change the doping within. We can bring in dopants like the lanthanides, the rare earths that we discussed in the previous talks, similar to what in the previous talks. So in this process, so what we do is it's similar to the process. We optimize the conditions within the chamber, and we also heat the substrate, in this case, silica-based glass. And so that you get this material to be mixed with the silica and essentially forming a new silicate glass at the surface. So the advantage of the process is that you can control where you want to modify on a substrate. So you can use basically a mask to control where you want to produce the changes. So here you can see the openings of the mask where the material is being diffused into the glass or doped into the glass. So in order to assess how the doped materials looks like, we can use what we call we can take a slice out of this glass, like slicing a cake. So here we use what we call the focused ion beam to cut a slice from the surface of the glass. So to get this out, you put basically a metallic coating at the surface, and the glass surface starts from here to there. So that is basically the doped layer, the modified layer, and that's the original glass. So that's we can analyze. We can produce this sample using focused ion beam milling, what we call FIB, and then you thin it down. You create a sample of that, and then you can put it in TEM and do an elemental analysis of that doped layer here. So here we can see we started with a silica glass. So that's why the silicon is present from the top to bottom. So you can see from there to here, you can see the silicon from there to here. So that's where the interface of the change that you see here. And then you got the tellurium, zinc, sodium, which all stops there. Yeah, there's some signal noise in there, but it's basically stops there. So it's all coming from zinc, sodium, terbium, and erbium. All these elements are coming from the target glass that we ablated and then used to modify this silica glass. So we can further look much detail into the glass. So you can see the doped layer. You can control the thickness of the layer by controlling the laser parameters. So that's a cross section shown in a higher magnification. And the application of this is, as I mentioned, we can increase the refractive index at the surface of the glass. So you create a layer of refractive index. So that can be used to, say, fabricate waveguides doped with rare earth ions and complex photonic circuits using that glass surface. So it can be also put on, say, silica on silicon materials as well. So here it shows that the material actually shows the erbium fluorescence when it is introduced into the silica. So this is a target glass fluorescence, it's broad, but once it is in silica, it is narrow. So we can use it for different applications. One of the applications what we are looking at is using the top layer as a method to as a sensor, and this is currently being investigated by this company, startup company from Leeds. It's called NIX. So they're using the doping concentration and things like that to use some sort of quantum interactions to detect glucose through the skin in the material. So it can be used as in wearable devices, as doped glasses, doped surfaces, and using its optical properties. Another application that we are looking at is strengthening of glass surface. Currently, as we know that most of the mobile screens are made of toughened glasses. Most of it is produced by Corning, which is the brand name called Gorilla Glass. So essentially, this works is like they use the toughening process used in those toughened glasses is introducing potassium into sodium into the by replacing sodium. So essentially, potassium is a large ion comparing to sodium. So it's a chemical process, and you replace the sodium with the potassium. You essentially create a stress layer at the surface, which provides the strength to the mobile glass screens in the current ion exchange based process. So we are proposing our idea to basically seal all the defects at the glass surface, so that the chances of breaking will be very low. Another thing we use it for is deposition. It's basically different from the doping process. So it's simple deposition process. So you can deposit, say, oxide materials like vanadium oxide, which is an interesting phase change material, which means that it can change its crystalline phase with the temperature or with the electrical by electrical excitation. So this is showing its phase change properties with the temperature, its resistivity change with the temperature. It's also being published recently. Another, we have also deposited titanium dioxide films, which are also interesting for many energy applications. So these are so any oxide materials, literally any material can be deposited using this material, using the process. But when most oxide and dielectric materials, they will be formed as nanoparticles, but we can form from a very small, by arranging smaller particles. So there are a number of other applications of femtosecond lasers, some of which is already covered in previous lectures, so in micromachining, surface structuring, and so on. Not going into the details of that, just trying to conclude. So these are the different areas of research at Leeds in my school, where applied photon science is involved in. So we are looking at laser processing of materials and different X-ray techniques for materials characterization, and also glass engineering, sensors, and imaging applications. So that's my group from a few years ago. Thanks to them all. Some of them already left. Some of them are still with me as postdocs. And that's all. Thanks to my funding agency, CPSRC, the Content Technology Hub, the NHS, and so on. Thank you.
Thank you, Jean, for this wonderful talk. And we have time for a few questions. It was on time.
You. Can I ask one question?
Yeah.
Jean, a fantastic talk. I enjoyed it. Okay. My first question is the interface. You have when you are firing your laser pulses onto a substrate or a substrate or a sample, the air to sample, that material property difference, is that critical for your thickness or the thin film development? if I have a soft material, will that be different from a harder material? That's the indirect question.
Yeah, so it's a very much material dependent process. We initially thought we can do it on any material, but that's not possible. So essentially, the deposited material should have chemical reaction with the substrate as well. So it's kind of a slow chemically induced process as well as so for example, if you deposit say phosphate glass, for example, on silica, we probably won't produce the same implanted layer, but the tellurides react with the silica. So it's a slow process, but it can be controlled once so it can initiate the process. Then you can control everything using the laser, the density of plasma, temperature, speed, and so on. Yeah.
Okay. And another quick one is on the TiO2. You last slide around, you put the TiO2 on it.
Yeah,
so we previously worked on converting laser-based anatase to rutile for TiO2.
Yeah.
While when you are depositing, during deposition, is it possible to convert or change the composition of some of the anatase to rutile? Because there is a lot of application around getting a particular percentage of anatase rutile. So is it possible to? Yeah. Okay.
Yes. Yeah. That paper actually talks about that. Yeah. Yeah.
Okay.
So we I think it's again to do. You can play with the substrate heating. So so you can form which phase to form. That's the same approach in the vanadium oxide as well. Usually this particular phase of vanadium oxide, which is very interesting, is called VO2M1 sort of phase, which is interesting for all the there's a lot of applications. It's very interesting material. So we got that particular phase by controlling the process. In short, it's basically the substrate heating. And then you have the temperature of the nanoparticles together with control it.
Yeah, we controlled using nanosecond pulses. We took anatase and converted rutile by focusing a laser beam onto it. So the changes because of the sudden heating, it changes to rutile.
Yeah. We kind of discussed a bit in that paper. So the vanadium oxide, actually we started with V2O5, which is a cheaper material, vanadium dioxide sort of, so that you ablate that and then you produce the VO2 phase. So that's there's another talk coming up, I think, in the electronic materials where we collaborated with Harriet Watt on that for microwave applications. So so it's interesting. You can change a lot of things. So even you can dope with another thing. So we recently did another work with doping tungsten into vanadium dioxide. So you change the transition temperature to near room temperature. So that has got many applications as well, I think.
Okay, thank you.
How well can you control the thickness and other properties of your material by adjusting maybe the laser parameters like pulse energy or pulse width?
Yeah. So we the thickness, one simple way is once you get the optimum process conditions, then you just change the time. So you grow the layer over a time, so you get thicker layer or thinner layer. You can also play with the fluence. So there is a dependence on the fluence as well on how fast, how deep, how fast you can grow a deep layer. So it's a deposition time and the fluence. The temperature, we had to find an optimal temperature and you keep it there.
And you talked about ultra-fast, X-ray processing of materials, isn't it? Something towards the end.
We are not doing any X-ray processing, but within my research team, the applied photon science research group, we collaborate with the diamond. Yes, you mentioned about it. So there's members in the group who work with the material characterization using the free electron laser there and so on. And we got the XPS facility here. So it's X-ray photoelectron spectroscopy.
Do you also have an free electron laser there?
Not here in the we got a collaboration with the diamond. Out of England.
Yeah.
I think you mentioned about
Yeah.
So I'm not directly involved. It's a colleague called Sven Schroeder. He is mainly doing that.
Okay. Any other questions? Maybe are there any in the chat? I think if there are no more questions,
it's not.
Let's thank Jin for this talk, and let me also thank your.
Excuse me.
There's a hand up. There's a hand up.
Okay.
Shamim.
Yeah. Hi. Thank you, sir, Professor, for the wonderful talk. Am I audible?
Yes. Go ahead. Yeah.
Yeah. Thank you for the wonderful talk. I have a couple of doubts over here. How homogeneous you can deposit the material, whether it is depending on the medium, I mean the temperature, which kind of medium you are working in, ambient atmosphere or in a vacuum chamber.
Yeah. So this is all done in vacuum chamber. In terms of the doping process, the homogeneity is quite good. That's simply looking at even the cross-section image. You don't see any detectable clustering.
It's a STEM image?
This is a TEM image. TEM.
TEM, okay, fine. Okay.
But there may be some clustering. So when we increase the rare earth concentration beyond certain levels, it's there in our published work. So there may be clusters of rare earths, but you cannot actually see here because. But we got the highest doping in terms of record, how much you can put rare earths without clustering. I think it is kind of aided by how you distribute the dopants. You're creating it in a kind of a slow process. So it's getting distributed more uniformly in the glass. But when you melt a glass, you haven't got any control over it. Yeah.
Okay. And how much focusing lens you are using? You are using a microscopic objective or a bigger focal length?
No, it's a long focal length. Yeah, it's a long focal length lens because you have to get the beam from outside to the chamber. Yeah.
And you are working in the vacuum now? Vacuum condition.
Yeah, it's in a vacuum chamber. So, but in principle, these processes can be done sort of 10 to the power.
We used to work this. I used to see this kind of material ablation, but in the atmosphere, and that is also depending when we are doing on the filamentation, whether it's playing a role. I mean, if we are keeping the sample at the different position of the filament, we can see the particle is removing at different phases. I mean, it's not homogeneously expanding to the atmosphere. So I have a doubt on this one, but still you are working in the vacuum chamber, it might not be a problem, no? I mean, if you are using the bigger focusing lens, you cannot avoid the filamentation.
Yeah, so that filamentation is happening in the target, isn't it? But we don't know what exactly happening. We are literally exploring the material. Yeah. So in terms of doing it at atmospheric pressure, if you do it at atmospheric pressure, you can't expand the plasma beyond certain length.
Yeah.
So then you can't deposit on a larger area as well.
Okay.
Yeah. So you still getting the material ablated, but be very close to the target.
Yeah, but we can easily see a lot of particles removing from the surface when we are focusing the high power.
Yeah. Yeah, that will still happen. So that's the micro machining is essentially that, isn't it? So
Okay.
So.
Okay. Thank you, Professor.
Yeah, thank you.
Okay, if there are no more questions, let's wind up the session. And thank you very much for all the speakers. All of them were almost on time, but we initially started a little bit late. But okay, this is the session was very interesting. For very good talks, and personally, I thank the organizers for this opportunity to interact with the speakers. Some of them, Jin and Prabhu, I knew from a long time, and I met two speakers on this conference, and that was also very good. Thank you very much. Thank you for inviting me. Thank you.
Yes, sir. Thank you. The session for today has come to an end. My sincere thanks to our Honorable Chair, Professor Riju C. Isaac, for conducting the session. My heartfelt gratitude to all our speakers, Professor Letitia Petit, Professor Emil Chitambo, Dr. Radhakrishnan Prabhu, and Professor Jin Jose for their engrossing and fascinating talks. Again, I extend my gratitude to the active viewers and listeners for making this a lively event. We have had an immensely rewarding and productive experience today, and I hope you have all had questions answered and new questions in the making, which of course is the indication of more knowledge. We appreciate the efforts of all who have been a part of this event today, and I wish with my whole heart that ICM-PMA will prove to be as effectual for everyone in the coming days. Before we end the meeting, I would like to give a few details about tomorrow's session. Tomorrow we move on to the third and fourth sessions of ICM-PMA, which will concern the topic energy materials. The third session, or the first session of the day, will start at 9:30 a.m. and end at 12:10 p.m., followed by a poster session. The fourth session of the conference, or the second session of the day, will begin at 2 p.m. and end at 4:30 p.m. The session from 2:30 p.m. to 4:30 p.m. will involve 3 parallel sessions for oral presentations on photonic materials and devices, biomaterials, and other materials. We desire all the oral presenters to be prepared for their respective presentations, and we wish you all the best. The link for each separate session will be available on the program schedule. Looking forward to a meeting as dynamic as we had today. Before leaving, we also request everyone to fill the feedback form available on the chat box. I hope you have all had a productive time. Good evening, and thank you to all. Have a nice day.
Thank you.
Just bring your